In the previous lecture, we have studied about the various methods of frequency FM demodulation, and there we have studied about single slope, balanced slope detector, Foster Silly discriminator, and ratio detector. Again, continuing with the frequency modulation, we have some important concept to be studied related to noise triangle, and then how this particular effect can be compensated by using pre-emphasis and de-emphasis network. So first we will understand what is the concept of noise triangle in FM and why we are talking about this particular topic here. So very important to remember, though we are saying that in the frequency modulation, amplitude does not affect, the change in the amplitude is not going to be there, but still the effect of noise will always be present in the FM, and this particular effect does not remain constant, meaning the noise is going to increase with the increase in the frequency of modulating signal. At higher frequency, the noise signal is going to affect more, and that is why we need to study that what is the effect of noise onto the frequency modulation signal. And therefore, we are defining again the formulas for the modulation index, and then we will understand that how this particular noise triangle is formed and what is the noise triangle. So here it is written that assuming the signal noise frequency, and that is going to modulate and that is going to affect the constant carrier signal, and the modulation index formula for FM, as we know, it is delta F divided by the modulating signal frequency. So if we consider the noise signal frequency, then formula will be MF is equal to delta F divided by Fn, where this Fn is called as signal noise frequency. The same formula can be modified if we consider a signal frequency. So we are considering a frequency which consists of a signal and it consists of a noise, and there we are finding out what is the signal to noise ratio. So in the previous slide, we have defined the modulation index considering noise frequency. In this slide, we are defining a modulation index considering signal frequency. So delta divided by Fs, where Fs is the signal frequency. And now, if we find out the formula for the signal to noise ratio, so it is equal to signal power divided by noise power. But what we are writing here is modulation index due to signal frequency divided by modulation index due to noise frequency. And this is how this particular formula is modified. MFS is the modulation index due to signal frequency, and MFN is the modulation index due to noise frequency. Now, if we observe this particular formula, so there you can see as the signal frequency increases, the modulation index due to signal frequency decreases. And therefore, it is written here as Fs increases, M of Fs decreases. And as per this particular formula, signal to noise ratio also decreases. These arrows are indicating upward means increasing, downward means decreasing, and therefore what we can conclude here that when the signal frequency increases, signal to noise ratio decreases. In the other words, the FM signals are going to be affected more at the higher signal frequency than the lower signal frequency. And therefore we are studying this particular concept of noise triangle. So what is the noise triangle? It is a plot of signal to noise ratio versus frequency, and this particular graph is not uniform, and therefore it is forming a shape of triangle, and that is why this particular graph is called as FM noise triangle. Again, it is the graph of signal to noise ratio versus frequency, and it is non-uniform, and that is why it is called as noise triangle, and that particular graph looks like this. So here you can see this is the graph of noise triangle, and why it is called as triangle, that is explained here. For reading this particular graph, on x-axis you can see there is frequency, carrier frequency Fc, On the other side, we have Fc plus Fm. On the lower side, we have Fc minus Fm. And here you can see two graphs which are shown with modulation index of 1 and modulation index of 5. And this particular graph is called as FM noise triangle. So you can see that when m is equal to 1, m is equal to 1 means lower modulation index. As per the previous formula, when the modulation index is low, meaning signal frequency is high. And therefore, you can see for m is equal to 1, the noise is affecting more. This is signal to noise ratio, and that particular you can see it is higher. For m is equal to 5, this particular graph is having lower noise, means the signal frequency is lower. So this particular graph is called as FM noise triangle. This particular shape looks like a triangle, and this particular is a plot of frequency versus signal to noise ratio, or you can say frequency versus the noise. And therefore we can say that from this particular graph we can say that higher modulating signal frequencies are more affected by the noise as compared to lower modulating signal frequency. And that is why we have to come up with some circuits which is going to compensate for this particular noise triangle. And there comes, and this particular graph again shows the noise triangle, wherein you can see if our this particular graph is our noise triangle from the previous slide. You can see there is a non-uniform noise level. At lower frequency, noise is 0, but when the frequency increases, the noise level also increases. And that is why at lower frequency you can see S by N is maximum, but when you go towards higher frequency, S by N is minimum. So if we keep our signal level uniform, then at lower frequency we have maximum signal to noise ratio. When you go towards higher side, the signal to noise ratio reduces. And that is why we need to change this particular uniform signal level such that our graph modifies like this. So here you can see this particular signal level is changed here. Here also it is changed, and therefore you can see at lower frequency the signal to noise ratio is maximum, and at higher frequency also the signal to noise ratio is maximum. And that is why it is giving uniform signal to noise ratio throughout the frequency spectrum span, which was not there in the earlier slide. And that is why you have non-uniform signal to noise ratio. So to have this particular signal to noise ratio, what we have to do? We have to boost the higher side frequencies such that our signal to noise ratio becomes uniform. And that particular work is done by a circuit which is called as pre-emphasis network. So what this pre-emphasis network will do, it is artificially boosting the high signal frequency, and definitely this will be done at the transmitter side. And since this is done before the FM modulation process, this particular name is given as pre-emphasis. So what is actually the pre-emphasis? It is typically a high pass filter, also called as differentiator, having some cutoff frequency. So as per our previous graph, we need to modify higher modulating signal frequency so that we get uniform signal to noise ratio, and this is what is done by pre-emphasis network, which will look like this. So here you can see this is a typical pre-emphasis network or a high pass filter or a differentiator, and this particular action is performed before FM modulation, and output of this will be the pre-emphasized output, means it is artificial boosting of only high frequency components, to be very clear, because we saw that high frequency components are more affected by the noise. In another book, we have diagram something like this, wherein you can see pre-emphasis network is constructed by using transistor, inductor, resistor, and typical values are given. L is equal to 750 millihenry, R is equal to 10 kilo ohm, and this is the formula for cutoff frequency. Naturally, when we have a filter, it will have some cutoff frequency, and formula is 1 upon 2 pi L by R. Now, pre-emphasis network is used at the transmitter. It is going to boost the high frequency component, artificial boosting, and definitely to compensate the effect of pre-emphasis, we have to use de-emphasis network at the receiver. So what is the function of de-emphasis network? Opposite to pre-emphasis. It is going to reduce the amplitude level. In other words, it is going to compensate for the high frequency signal by same amount as it was increased by pre-emphasis. And this particular process is done at the receiver, but it is after demodulation, and that is why the name is given as de-emphasis. De-emphasis is the opposite of pre-emphasis. If pre-emphasis is high pass filter, then de-emphasis is going to be a low pass filter or integrator having a cutoff frequency of, this is a typical look of a de-emphasis network. After FM demodulation, there is a RC network which is acting as a low pass filter or an integrator or a de-emphasis network, and the formula for it is 1 upon 2 pi RC. This is the formula for cutoff frequency, and with typical values the circuit is designed to give a RC time constant of 75 microsecond, and when you substitute that in this formula, you will be getting a cutoff frequency of 2.12 kilohertz, which you are able to see here. So this is a typical characteristics of a pre-emphasis and de-emphasis network. Pre-emphasis is a high pass filter, so after certain frequency it will increase the gain, and de-emphasis is a low pass filter, so after certain frequency it is going to decrease the gain, and this particular frequency is 2.12 kilohertz as per the previous diagram and typical component values which they have assumed. So this is how the pre-emphasis and de-emphasis network is going to compensate for the effect of noise on the frequency modulated signal. To summarize, why we go for pre-emphasis and de-emphasis network is that the higher modulating signal is going to be affected more by the noise, and that is why we need to artificially boost the higher modulating signal frequency such that we get uniform signal to noise ratio throughout the frequency spectrum, and this is done by pre-emphasis network. And to compensate for the artificial boosting at the receiver side, we are using de-emphasis network so as to compensate for this. So pre-emphasis network is a high pass filter, de-emphasis network is a low pass filter, and after certain frequency, which we call it as cutoff frequency, the pre-emphasis network and de-emphasis network starts working. And this is what is the concept of noise triangle, pre-emphasis and de-emphasis network. In the next lecture, we will be able to study about the radio receivers, which will be chapter